Hi everyone, let's again consider the simple mass spring system. In this section, I want to look into its energy as it moves in simple harmonic motion. This is a system with no non-conservative forces, so the total mechanical energy of the system is conserved. The Hooke's law restoring force is a conservative force that changes the elastic potential energy of the system. Elastic potential energy is the energy stored in a stretched or compressed spring, and it's given here, it's US, and it's given by 1/2 kx squared, where k is the spring constant in newtons per meter and x is the displacement in meters. As the object moves, it also has an energy associated with its motion, which is kinetic energy k, and that's 1/2 m, mass in kilograms, times v squared, that's the speed in meters per second. And energy is measured in joules. E is the total energy, which is the sum of the kinetic and the elastic potential energy. So as the system moves, its total energy will remain constant, but the energy of the system will exchange between kinetic and elastic potential. At the turning points, we'll have the maximum elastic potential energy when the spring is at its maximum stretch or compression. So that's at A and negative A. Then we know that when it's at 0, x is 0, so the elastic potential energy is 0 there. And we can talk about the same with kinetic energy. So kinetic energy will be highest when the speed is the greatest. We know that's the opposite to the potential, so the kinetic energy will be maximum as the object passes through equilibrium in both directions, and it will be a minimum when the object stops both at x equals a and x equals negative a at its turning points. You might have seen a graph like this before. This is the energy graph for this object, and it shows how the energy varies with respect to displacement. So I have the turning points marked here. This line is the total energy here, and then this is the potential energy, specifically of the elastic potential energy in this case. So we see that it's a maximum and equal to the total energy at the turning points. The system doesn't exist above that total energy line. So we have the two turning points here, and then we have the minimum at x equals 0 as expected. Now the kinetic energy will be maximum at that point, and you can picture the kinetic energy on the graph as the vertical height between the total energy line and the potential energy line, since it is the difference between the two if you rearrange. So it's important to understand where each type of energy is the maximum and where it is the minimum. I want to now use the expression for energy to come up with a value for the total energy of the system. So our energy is 1/2 mv squared plus 1/2 kx squared. There's two ways to show this. The first method I'm about to do is a little bit more complicated. The second one's shorter, so we'll do the long one first. Alright, so I want to plug in the expressions for x and v that we have from our previous section into this total energy equation. We also have omega squared equals k over m. So I'm going to plug them in. We have E equals 1/2 m negative omega a sine omega t plus phi squared plus 1/2 k a cos omega t plus phi squared. Now to simplify, this will be 1/2 m omega squared a squared sine squared omega t plus phi plus 1/2 k a squared cos squared omega t plus phi. Now looking at this, I want to use that identity we've used before where sine squared omega t plus phi plus cos squared equals 1. So let's check if these coefficients are the same. 1/2 ka squared is here. This is 1/2 m omega squared a squared. Now if I plug in, I have 1/2 m, I'm plugging in for omega squared, k over m, a squared. And then just filling in the rest as before. This does cancel, so m cancels, and we do have 1/2 ka squared in front. So 1/2 ka squared, and then sine squared omega t plus phi plus cos squared omega t plus phi. And all of that equals 1. So then what we have is that E equals 1/2 k a squared. And this is an important result because this gives us the total energy for the system. And this is a constant. We just have the spring constant k and then the amplitude a squared. So this is always true. At any point, the total energy of the system is equal to 1/2 ka squared. Okay, now I'm going to show you how to prove this a second way. Method 2, here's our mass on the spring. Okay, so we know the total energy is 1/2 mv squared plus 1/2 kx squared. And let's consider the turning points. Let's consider x equals a, where I've drawn it here. At that point, we have x equals a, and then we have v equals 0 because it's a turning point. So let's plug those in. We'll get E equals 1/2 m 0 squared plus 1/2 k a squared. And so of course that first term is 0, and we get E equals 1/2 k a squared. So we've found the energy at this point, and the total energy at x equals a is 1/2 ka squared. Now, that's really not proof on its own, but what we have to add is that this is simple harmonic motion, so the total energy is conserved, which means that if this is the total energy at one point, it must be the total energy at every point. So this must be the total energy everywhere. And by everywhere, I mean at all x values. So that is a bit quicker, but both methods show us the same value for the total energy, 1/2 ka squared. Now that we know the total energy, we can use that to find the speed as a function of position. So find the speed at any position using this energy. We just need to equate the total energy, 1/2 ka squared, to the rest of the equation. So here you can see that if you knew x, you could solve for v, because that would be our only other unknown as long as we know the spring constant and the mass for the system. So let's just solve for that so that we have an expression, but you can do it every time you have an example. So all of these 1/2 factors cancel. And then I have mv squared equals ka squared minus kx squared. So we'll get v squared equals k over m, a squared minus x squared. So v will be plus or minus the root of k over m, a squared minus x squared. And then with that, you could solve for the speed. And it's giving us plus or minus, so actually it will give us the velocity as well, as long as you account for the sign and look at where it's moving at that position. A 326 gram object is attached to a spring and executes simple harmonic motion with a period of 0.250 seconds. If the total energy of the system is 5.83 joules, find A, the maximum speed of the object, B, the force constant of the spring, and C, the amplitude of the oscillation. Okay, so for A, we want the maximum speed. So looking at this equation for the energy of the system, we know that Vmax occurs when x equals 0. Logically, we know that it's moving the fastest when it's moving through its equilibrium position. However, we can also see that from this equation here, that when we have x equals 0, the speed will be the highest since E is constant. So then we get V max will equal the root of 2e over m, since this term is 0. So that's the square root of 2 times 5.83 joules over 0.326 kilograms. So 5.98 meters per second. Okay, so for B we want to find the spring constant, and to do that we can use the period. So we've done something like this before. The period is 2 pi over omega, so 2 pi root m over k, and squaring both sides I have t squared equals 4 pi squared m over k. So k equals 4 pi squared m over t squared. 4 pi squared, 0.326 kilograms over 0.250 seconds squared, which is 206 newtons per meter. Okay, and the last part is the amplitude of the oscillation. For this we can use the total energy. So looking here again, we know that our total energy that we're given is equal to 1/2 Ka squared, as we proved twice. So solving for the amplitude, we have the root of 2e over k. So the root of 2.583 joules over 206 newtons per meter, which is an amplitude of 0.238 meters. Example 7, a 2 kilogram object is attached to a spring and placed on a horizontal smooth surface. A horizontal force of 20 newtons is required to hold the object at rest when it is pulled 0.2 meter from its equilibrium position. The object is released from rest from this position and undergoes simple harmonic motion. Find A, the force constant of the spring and the frequency of the oscillation, B, the total energy of the oscillating system, C, the speed and acceleration of the object when its position is equal to 1/3 of its maximum value. Alright, so we're given this horizontal force that holds it in place, so that in part A we can use Hooke's law and Newton's first law in order to find the spring constant. So Newton's first law, the sum of the x forces are equal to 0, which means that the force applied is equal to the spring force. So we have kx equals Fa, and then k will be Fa over x. So that's 20 newtons over 0.2 meters, which gives 100 newtons per meter. Then with that, we need the spring constant so that we can find the frequency of the system. Frequency is 1 over the period, so the inverse of the relationship that we've seen before, or omega over 2 pi. So that's 1 over 2 pi root k over m when you plug in omega equals root k over m. So 1 over 2 pi, the root of 100 newtons per meter over 2 kilograms gives me 1.125 hertz. Okay, and now we can find the total energy of the system, which is part B. Using the equation we have 1/2 Ka squared, 1/2 times 100 newtons per meter times 0.2 meters squared, 2 joules. And lastly, now we have a position of x equals 1/3 A, since it's equal to 1/3 of its maximum value. And then I showed you recently how to come up with this equation for the velocity. So you can start with the equation for energy, which I would do if we hadn't just done this. So V equals the root of k over m a squared minus x squared. and then we can plug in. So V will be the root of K over M, and then I'm going to have A squared minus 1/3 A squared. So in here I'm going to have 1 minus 1 over 9, so that's 8 over 9. So root K over M times root 8 over 9A. And then plugging that in, root of 100 newtons per meter over 2 kilograms, root 8 over 9 times 0.2 meters is 1.33 meters per second. So that's the speed at that point. And we want the acceleration. So the acceleration now can come from Newton's second law. Sum of those x forces equals ma. So kx, it's been released at this point and it is in simple harmonic motion, so there's no longer an applied force. So we'll have A equals kx over m. So that's 100 newtons per meter times 1/3 of 0.2 meters, since it's still at 1/3 A, over 2 kilograms, to give an acceleration of 3.33 meters per second squared at that point. Systems in simple harmonic motion are called bound systems because they're constrained within the turning points. So far we've focused on the mass on a spring, but we can apply this knowledge of simple harmonic motion to analyze other systems that are acted on by a linear restoring force in periodic motion. And we'll look at that in the next section. We know that simple harmonic motion is an idealization because any real-life system would have some losses in energy. However, there are some situations where it's a good approximation, and some examples are the vibrations in airplane wings, or 2 atoms in a molecule, or electrons in an electric circuit. So after we consider other cases of simple harmonic motion, we'll look at applying this to real-life systems as well.